So we did a little bit of an overview of the kind of reasons we might want a trusted execution environment, what enclaves are for, why we need to implement them, and the different sort of features that they might implement. We're going to look at some of these things in a specific case study with RISC-V, and then just show some really simple examples of how this stuff is done in a real-world environment. So RISC-V's trusted environment is called Keystone. It's an open source enclave system that implements features that are similar on a lot of other things, right? Intel has their own proprietary systems. All of these manufacturers have their proprietary systems, but if you want to really understand how it works under the hood, an open source system is nice because you can actually see all the details. You can see all the spec documents, right? It's built on of RISC-V, which means like RISC-V, it has a modular design. Features can be added or removed, and it uses RISC-V primitives where it is available. So some of the things we talk about, if you've done RISC-V, you might be familiar with it. There is a site, keystoneenclave.org. The rest of this video is going to steal slides from there, but it's open source, and so they say, share the slides, and so that's fine. So this is, again, really simple. It's not going to get into too much detail, but I want to walk through really quickly what that means, what it looks like. So if you have a hardware system that's running RISC-V that you want to implement enclaves on, here are the different things you need to implement. Right? You need a physical memory protection, which we'll talk about. You need user modes. We've already talked about this in other videos, right? When you are running your code, you're in user mode. When an interrupt happens, often when you get interrupted, the system mode, S mode, will be implemented and other features are available. I don't have access in U mode to some of the features that there is available in S mode. It can do more things. And then M mode is the machine mode. It is the most high privilege, the most protected, the most secure. Then there are things like an entropy source available at boot. This is so that if you are doing encryption and decryption, you need to have some source of randomness so that you can actually do these encryptions and decryptions. And then the root of trust, right? This is this hardware box that the user and the system and everybody knows cannot be modified, and it's for signing the security measures, and you know for sure that it's going to be working. And then you have the memory encryption engine that we talked about and all the other things. So just the example for memory isolation is probably the nicest one to go through. We're going to use a system called physical memory protection. This is the PMP. This is the RISC-V version of memory isolation. And it's implemented with a series of registers that basically show whoever's operating right now what parts of memory you're allowed to access. And so if the register, the PMP register, tells you that you can access this chunk of memory, great. If not, you are prevented from accessing it at the hardware level. So the implementation of these registers is controlled by the secure monitor. This is the thing that actually is allowed to change these registers so that you can open and close different chunks of memory. So what does that look like? So here are the series of registers, and then each register has a little window, a mode window. This is R, W, and X, right? Read, write, or execute. This is the classic Unix permissions that give you access to whether or not you can run this software. So by default, the SM software is inaccessible. When the SM boots, it's going to run things at the lowest level, but it's going to always protect the memory areas. No other system can actually run those areas. But then when you want to set up some enclaves, each enclave has a chunk of memory allocated and a read, write, execute set of bits in the PMP that corresponds to that chunk of memory. So if I'm running in the operating system right now, right, I'm in the OS, I'm running around, I can't access Enclave 1 or Enclave 2 or the secure memory because they're blocked from me by these physical memory registers. If I want to shift control, right, do a context switch into a process that's going to run in an enclave, I'm going to give access to a user system that's going to run in an enclave, then I swap. And by I mean the system monitor, right? The lowest level security monitor, even the operating system can't mess with this. Swaps out those permission bits so that the operating system no longer has access and only the enclave has access. So the enclave, when it starts to run, it has access to this memory. Everything else is blocked off. No other memory is accessible at the hardware level because these registers are blocking that ever. And the neat thing about this is you have a series of registers. If you want to instantiate a new enclave, you just populate a new register right? You populate a new register, and that gives you access to a new chunk of memory. And perhaps there's a shared memory that is accessible by many enclaves, right? This would be considered an unsecure buffer, but it can be accessed at the same time as the enclave memory can be accessed. So each little chunk of memory is either accessible or not accessible based on the physical memory registers that provide that access, and those are controlled exclusively by the system monitor, SM. If you are looking at what the runtimes look like, this is going to be a little tiny chunk of code that is going to be implemented in any of these enclaves that gives the enclaves some basic functionality. It's going to allow some level of system calls and traps. It's going to allow some level of thread and page management. But again, it is protected and only instantiated by the security monitor. The reusability means that you can check that code and make sure it's doing what you want to do. But essentially, it protects your system and allows you to have some functionality from your system. And then finally, a little tiny detail on remote attestation, right? This is the collection of processes that allow you to report back externally and say, yes, everything works the way it's supposed to. This is done in real time as the enclave is instantiated and then decommissioned. The security monitor is going to measure this enclave as it's instantiated, as it's decommissioned, to make sure that everything worked the way it was supposed to. And then it can submit an attestation that says, yes, this was secure, or no, there were some problems, right? And this enclave report is what gets produced, signed by the security monitor that says, yeah, everything was fine. That gets sent back to the user and says, yes, your operation completed successfully. Last tiny thing is what happens to interrupts and exceptions, right? This is the mechanism by which a computer stops one process and starts another, and it is critical to the operation of a machine because you might have things that you want to do every clock cycle, or things that you want to do when the user presses a button, or who knows what, right? There are physical things that happen in the world that require you to transfer control from one thing to another. If this were to happen in an enclave, really bad things would happen. So the interrupt process is redeveloped and restricted strictly to the security monitor, the security manager. This adds a little bit of time and overhead to the process, but it ensures that things are secure. So I'm operating in an enclave, things are trucking along, and there's an interrupt. Well, what that happens is instantly my process is halted. My pipeline is drained, my register values are preserved on a stack, and then control is transferred to the secure monitor. Now, how do I get stuff back? How would I start back again? Well, the secure monitor is going to store my program counter, my stack pointer, and any status registers so that I can start up again, but it's storing that in its secure memory, its location, because it is the trusted agent, right? So when it wants to start up my enclave again, it's going to transfer back my program counter, my stack pointer, my control, my status registers, so that I can carry on where I was and not even know that I was interrupted. But in the process of being interrupted, when the control transfers to the secure monitor, again, we store these registers. Then once it has stored the status registers for the context that I need to restore, everything's wiped out. Wipes out the registers, wipes out any information that might be able to be used to leak from one place to another. And then we know that you're not going to be able to share information through those side channels that we saw in the other videos. So that's just a really simple and quick overview of the kind of features that need to be implemented if you're going to be doing enclaves and secure memory in a shared system.